Welcome to Celestial Sleep, where the mysteries of the universe become your pathway to peaceful sleep. Tonight, we embark on a deliberately boring journey through the complete life cycle of stars. From their humble beginnings as scattered gas in molecular clouds to their eventual demise as supernovae, white dwarfs, or black holes, we will explore every tedious detail of stellar evolution at a pace designed to help you drift gently into slumber. As you listen to this scientifically accurate but intentionally monotonous explanation of how stars are born, live, and die, allow your mind to wander among the stars while your body relaxes. The universe operates on timescales of millions and billions of years, and tonight we'll match that unhurried pace with our exploration of cosmic phenomena. But before we begin, I'd love to know, where in the universe are you listening from? Drop a comment with your location and current time. Are you watching under a starry sky, curled up in bed, or maybe even during a lunch break? And if you enjoy drifting off to the calm, methodical rhythms of space, consider subscribing to Celestial Sleep. Now feel free to close your eyes as we begin our journey through the life cycle of stars. Whether you stay awake for the entire narrative or drift off to sleep partway through, rest assured that the stars will continue their slow, predictable cycles regardless of who is watching. Before we delve into the specifics of stellar evolution, let's take a moment to consider the vastness of the cosmos in which these processes unfold. Our observable universe spans approximately 93 billion light-years in diameter, containing an estimated 2 trillion galaxies. Each of these galaxies contains billions or even trillions of stars, each following the life cycle we will describe tonight. Our own galaxy, the Milky Way, is a barred spiral galaxy containing between 100 and 400 billion stars. It spans about 100,000 light-years across and has a thickness of about 1,000 light-years. Our Sun is located in one of the spiral arms, about 26,000 light-years from the galactic center. The stars we see in the night sky are merely a tiny fraction of the stars in our galaxy and an infinitesimal fraction of the stars in the universe. Yet each follows the same basic principles of physics, the same fundamental processes of stellar evolution that we will explore tonight. The study of stellar evolution is a relatively recent development in human history. While humans have observed and cataloged stars for thousands of years, it was only in the 19th and 20th centuries that we began to understand the processes that drive their formation, life, and death. The development of spectroscopy in the 19th century allowed astronomers to determine the composition of stars by analyzing the light they emit. The development of quantum mechanics and nuclear physics in the early 20th century provided the theoretical framework for understanding the nuclear reactions that power stars. In the mid-20th century, astronomers like Subrahmanyan Chandrasekhar, Fred Hoyle, and Hans Bethe made crucial contributions to our understanding of stellar evolution. Their work, along with that of many others, has given us the comprehensive picture of stellar life cycles that we will explore tonight. As we embark on this journey, remember that the processes we describe unfold over millions or billions of years. The stars we see in the night sky are like snapshots, each capturing a different moment in the grand cycle of stellar evolution. Some are just being born in vast molecular clouds, others are in the prime of their lives on the main sequence, and still others are approaching their end as red giants or supernovae. Now, let us begin our exploration of stellar evolution with the first stage, the vast, cold molecular clouds where stars are born. Part 1: Molecular Clouds, the Stellar Nurseries. Our story begins in the vast, cold expanses between existing stars, where enormous clouds of molecular hydrogen float in seemingly empty space. These molecular clouds, sometimes called stellar nurseries, are the birthplaces of all stars in our universe. They are quite literally the beginning of our story. These clouds are not particularly dense by earthly standards. If you were somehow able to stand inside one, you might not even notice the gas around you. The typical molecular cloud has a density of only about 100 to 1,000 molecules per cubic centimeter. For comparison, the air you're breathing right now contains approximately 10 quintillion molecules per cubic centimeter. That's 10 followed by 19 zeros. So these clouds are incredibly diffuse, about a trillion times less dense than the air in your bedroom. Despite this remarkably low-density, molecular clouds contain enormous amounts of matter because they are unimaginably vast. A typical molecular cloud might span 50 to 500 light-years across. To put that in perspective, a single light-year is approximately 9.5 trillion kilometers, or about 5.9 trillion miles. So these clouds can span hundreds of trillions of kilometers, containing enough material to form thousands or even millions of stars. The temperature within these clouds is extraordinarily cold, typically ranging from about 10 to 20 Kelvin. That's approximately minus 263 to minus 253 degrees Celsius, or minus 441 to minus 423 degrees Fahrenheit. At these temperatures, almost everything except hydrogen and helium would be frozen solid if there were enough particles to form solids at all. Molecular clouds are composed primarily of molecular hydrogen, which makes up about 74% of their mass. Helium accounts for about 25%, while all other elements, what astronomers somewhat dismissively call metals, make up the remaining 1%. These other elements include carbon, nitrogen, oxygen, silicon, iron, and all the other elements of the periodic table. The clouds are not uniform in density. They contain regions of slightly higher density called clumps or cores. These denser regions are where star formation will eventually begin, though the process is excruciatingly slow by human standards. Let's take a moment to consider the scale of these molecular clouds in more detail. The largest molecular cloud in our galaxy is the Sagittarius B2 cloud, located near the center of the Milky Way. It spans about 150 light-years across and contains enough material to form about 10 million stars like our Sun. Despite its enormous size, it would appear as just a dark patch against the background of stars if we could view it from outside our galaxy. Closer to home, the Orion Molecular Cloud Complex is one of the most active star-forming regions in our local neighborhood. Located about 1,500 light-years from Earth, it spans about 240 light-years across and contains several distinct molecular clouds. The Great Orion Nebula, visible to the naked eye as a fuzzy patch in the constellation Orion, is just a small part of this vast complex. The Taurus Molecular Cloud, located about 430 light-years from Earth, is another nearby star-forming region. It spans about 100 light-years across and contains enough material to form about 10,000 stars like our Sun. It's home to a number of young stars and protostars, including the famous T Tauri, which gives its name to a class of young, variable stars. The composition of molecular clouds is not limited to simple molecules like hydrogen and helium. Astronomers have detected more than 200 different molecular species in these clouds, including water, ammonia, formaldehyde, and even complex organic molecules like ethanol and acetone. These molecules form on the surfaces of dust grains, which provide a substrate for chemical reactions that would be unlikely to occur in the gas phase. The dust in molecular clouds, while only constituting about 1% of the cloud's mass, plays a crucial role in star formation. Dust grains absorb and scatter light, making the clouds appear dark when viewed against a bright background. This is why molecular clouds are often visible as dark patches in the night sky, particularly along the band of the Milky Way. Dust grains also play a crucial role in cooling the cloud. They absorb energy and radiate it away as infrared radiation, which can escape the cloud more easily than visible light. This cooling is essential for the cloud to collapse and form stars, as we'll discuss in more detail later. The dust in molecular clouds is composed primarily of silicates and carbonaceous materials, similar to the dust in our own solar system. These dust grains are incredibly small, typically less than a micrometer in diameter. Despite their small size, they have a large surface area relative to their volume, making them efficient catalysts for chemical reactions. The formation of molecular clouds is a complex process that is not fully understood. They are thought to form from the diffuse atomic hydrogen that permeates the interstellar medium. This atomic hydrogen can be compressed by various processes, including the passage of spiral density waves in the galaxy, the expansion of supernova remnants, or the collision of gas clouds. As the atomic hydrogen is compressed, it becomes dense enough for molecules to form. The most abundant molecule is molecular hydrogen, H2, which forms when two hydrogen atoms combine on the surface of a dust grain. The dust grain absorbs the energy released by this reaction, preventing the newly formed molecule from immediately breaking apart. Once molecular hydrogen has formed, the cloud can cool more efficiently, as molecular hydrogen can radiate energy through rotational and vibrational transitions. This cooling allows the cloud to contract further, increasing its density and promoting the formation of more molecules. The formation of a molecular cloud is a gradual process that unfolds over millions of years. Once formed, a molecular cloud can persist for tens of millions of years before it is dispersed by the energy input from the stars that form within it. Molecular clouds are not isolated entities. They are part of the larger cycle of matter in the galaxy, known as the galactic ecology. Material from old stars is returned to the interstellar medium through stellar winds and supernova explosions. This material, enriched with heavy elements produced in the stars, eventually becomes part of new molecular clouds, which in turn form new stars and planets. This cycle has been ongoing since the formation of the first stars in the universe, about 100 million years after the Big Bang. Each generation of stars enriches the interstellar medium with heavier elements, leading to a gradual increase in the abundance of these elements over cosmic time. The molecular clouds we observe today are the result of billions of years of this cosmic recycling. They contain the ashes of countless generations of stars, transformed into the raw material for new stars and planetary systems. As we continue our unhurried journey through the life cycle of stars, let us now examine how these diffuse clouds begin the long, slow process of collapsing to form protostars. Part 2: Cloud Collapse and Fragmentation. The transformation from a diffuse molecular cloud to a collection of stars is a gradual process that unfolds over millions of years. It begins with a disturbance, perhaps a shock wave from a nearby supernova, the pressure wave from a spiral arm of the galaxy passing through, or simply a random fluctuation in the cloud's density. Whatever the cause, this disturbance creates regions within the cloud where the density is slightly higher than in surrounding areas. These regions have slightly stronger gravitational attraction than their surroundings, causing them to draw in more material, which further increases their gravitational pull. This self-reinforcing process is known as gravitational collapse. For a region to begin collapsing, its gravitational energy must exceed its thermal energy, the random motions of the gas molecules that would otherwise cause the region to expand. This balance is described by the Jeans criterion, named after the British physicist Sir James Jeans, who first derived it mathematically in 1902. The Jeans mass, the minimum mass required for gravitational collapse to begin, depends on the temperature and density of the cloud. For typical molecular cloud conditions, the gene's mass is about 1 to 10 solar masses. Regions with less mass than this will not collapse under their own gravity. As a region begins to collapse, it doesn't remain as a single entity. Instead, it fragments into smaller and smaller pieces. This fragmentation occurs because smaller regions can collapse faster than larger ones, and because rotation and turbulence within the cloud create substructures. The process of fragmentation is complex and not fully understood, involving the interplay of gravity, thermal pressure, magnetic fields, and turbulence. Numerical simulations suggest that a collapsing cloud typically fragments into dozens or hundreds of smaller cores, each of which may eventually form a star or a small group of stars. The role of magnetic fields in cloud collapse and fragmentation is particularly complex. Magnetic fields can provide support against gravitational collapse, potentially preventing or delaying star formation. However, the magnetic field can gradually diffuse out of the cloud through a process known as ambipolar diffusion, allowing collapse to proceed. Ambipolar diffusion occurs because the magnetic field is coupled to the charged particles in the cloud, primarily electrons and ions, but not to the neutral particles, primarily molecular hydrogen. The neutral particles can gradually drift through the magnetic field, accumulating in the denser regions of the cloud. Eventually, the gravitational pull of these denser regions can overcome the magnetic support, leading to collapse. The timescale for ambipolar diffusion is typically a few million years, which is consistent with the observed lifetimes of molecular clouds. This suggests that magnetic fields play a significant role in regulating star formation, preventing molecular clouds from collapsing too quickly and forming stars too rapidly. Turbulence also plays a crucial role in cloud collapse and fragmentation. Turbulence refers to the random, chaotic motions of the gas within the cloud. These motions can provide support against gravitational collapse, similar to thermal pressure or magnetic fields. However, turbulence also creates density fluctuations within the cloud, which can serve as seeds for gravitational collapse. The interplay between turbulence and gravity is complex and not fully understood. Numerical simulations suggest that turbulence can both promote and inhibit star formation, depending on the specific conditions. In general, turbulence tends to promote the formation of filamentary structures within molecular clouds, which are often observed in real molecular clouds. These filaments are regions where the gas has been compressed by turbulent motions. They can be hundreds of times denser than the surrounding cloud, making them prime sites for star formation. Indeed, observations show that protostars are often found along these filaments, like beads on a string. The collapse of a cloud fragment is not a smooth, continuous process. It proceeds in fits and starts, with periods of rapid accretion followed by relative quiescence. This variability is reflected in the brightness of protostars, which can fluctuate significantly over timescales of years to decades. As the collapse continues, the density and temperature at the center of each fragment increase. When the central temperature reaches about 2000 Kelvin, molecular hydrogen begins to dissociate into atomic hydrogen, absorbing energy and temporarily stalling the temperature increase. Once the hydrogen is fully dissociated, the temperature begins to rise again. At a temperature of about 10,000 Kelvin, hydrogen atoms begin to ionize, again absorbing energy and temporarily halting the temperature increase. Once the hydrogen is fully ionized, the temperature rises rapidly, eventually reaching millions of degrees in the core of the protostar. Throughout this process, the outer layers of the fragment continue to fall inward, adding mass to the growing protostar. This infall can continue for hundreds of thousands or even millions of years, gradually building up the mass of the star. The rate of this infall depends on the temperature of the gas, which in turn depends on how efficiently it can cool by radiating away energy. In the outer parts of the cloud, where the gas is transparent to infrared radiation, cooling is efficient and the infall proceeds relatively quickly. In the denser inner regions, where the gas is opaque to its own radiation, cooling is less efficient and the infall slows. The collapse of a cloud fragment is not spherically symmetric. The fragment has some initial rotation, which becomes amplified as it contracts, just as a spinning ice skater rotates faster when pulling in their arms. This rotation causes the fragment to flatten into a disc-like structure, with material preferentially falling onto this disk, rather than directly onto the central protostar. This disk, known as a protoplanetary disk or proplyd, will eventually give rise to a planetary system. The formation of such disks is a natural consequence of angular momentum conservation during the collapse process. As the cloud contracts, its rotation rate increases to conserve angular momentum, leading to the formation of a flattened disk. The size of the disk depends on the initial angular momentum of the cloud fragment. Typical protoplanetary disks have radii of a few hundred astronomical units, though they can be much larger or smaller depending on the specific conditions. The disk is not uniform in density or temperature. It is denser and hotter near the central protostar, and less dense and cooler at larger radii. This gradient in conditions will eventually lead to the formation of different types of planets at different distances from the star, as we observe in our own solar system. The formation of a protoplanetary disk marks the transition from the cloud collapse phase to the protostar phase of stellar evolution. As we continue our deliberately monotonous exploration of stellar evolution, let us now turn our attention to the formation and evolution of protostars. Part 3: Protostar Formation. A protostar is an early stage in the process of stellar formation. It is not yet a true star because nuclear fusion has not begun in its core. Instead, it derives its energy from gravitational contraction. As material falls inward, gravitational potential energy is converted to thermal energy, causing the protostar to heat up and emit radiation. The transition from a collapsing cloud fragment to a protostar is gradual and not marked by any single event. Generally, astronomers consider a dense core to have become a protostar when it has developed a well-defined central object that is accreting material from its surrounding envelope. Protostars are classified into several stages based on their spectral energy distribution, the amount of energy they emit at different wavelengths. These stages, designated Class 0 through Class III, represent a progression from deeply embedded objects visible only at far-infrared and submillimeter wavelengths to more evolved objects visible at near-infrared and optical wavelengths. Class 0 protostars are the youngest, with ages less than about 10,000 years. They are so deeply embedded in their parent cloud that they are invisible at wavelengths shorter than about 20 micrometers. Most of their luminosity comes from the accretion of material onto the central object, rather than from the central object itself. The central object in a Class 0 protostar is still quite small, containing less than half of the mass that will eventually make up the final star. The rest of the mass is still in the surrounding envelope, slowly falling inward. The temperature at the center of a Class 0 protostar is typically a few thousand Kelvin, not yet hot enough for nuclear fusion to begin. Let's delve deeper into the properties of Class 0 protostars. These objects are characterized by a spectral energy distribution that peaks in the far-infrared or submillimeter range, typically around 100 to 300 micrometers. This peak corresponds to a blackbody temperature of about 10 to 30 Kelvin, reflecting the temperature of the dust in the surrounding envelope. The total luminosity of a Class 0 protostar is typically a few solar luminosities, though it can vary significantly depending on the mass of the protostar and the rate at which it is accreting material. This luminosity is primarily generated by the accretion process, as material from the surrounding envelope falls onto the central object. The accretion rate for a Class 0 protostar is typically about 10 to 10^4 solar masses per year. At this rate, it would take about 10,000 to 100,000 years to accumulate a solar mass of material. This is consistent with the estimated lifetimes of Class 0 protostars. Class 0 protostars are often associated with powerful bipolar outflows. These outflows, directed along the rotation axis of the protostar, can extend for light years and play an important role in removing angular momentum from the system, allowing accretion to continue. The outflows consist of two components: a highly collimated jet moving at hundreds of kilometers per second, and a wider-angle wind moving at tens of kilometers per second. The jet is thought to be driven by magnetic fields in the inner part of the circumstellar disk, while the wind may be driven by radiation pressure or magnetocentrifugal forces from the outer disk. These outflows can have a significant impact on the surrounding molecular cloud, injecting energy and momentum into the cloud, and potentially triggering the formation of additional stars. They can also clear out cavities in the cloud, allowing radiation from the protostar to escape more easily. As accretion continues, the protostar evolves into a Class I object, typically after about 100,000 years. By this stage, the central object contains more mass than the surrounding envelope, and it has developed a substantial circumstellar disk. The protostar is still heavily obscured at optical wavelengths, but may be visible in the near-infrared. Class I protostars have spectral energy distributions that peak in the far infrared, typically around 100 micrometers, corresponding to a blackbody temperature of about 30 Kelvin. However, they also show significant emission at shorter wavelengths, indicating the presence of warmer dust closer to the central object. The total luminosity of a Class I protostar is typically a few solar luminosities, similar to a Class 0 protostar. However, a larger fraction of this luminosity comes from the central object itself, rather than from the accretion process. The accretion rate for a Class I protostar is typically about 10^6 to 10 solar masses per year, an order of magnitude lower than for a Class 0 protostar. This decrease in the accretion rate reflects the depletion of the surrounding envelope, as material is either accreted onto the central object or dispersed by the outflows. Class I protostars continue to drive powerful outflows, though these may be less collimated than the outflows from Class 0 protostars. The outflows can still extend for light years and have a significant impact on the surrounding molecular cloud. The circumstellar disk around a Class I protostar is more developed than around a Class 0 protostar. It typically has a radius of a few hundred astronomical units and contains a significant fraction of the total system mass, perhaps 10% to 20%. The disk is not passive, but is actively accreting material onto the central object. This accretion is thought to be driven by various instabilities in the disk, including gravitational instabilities, magnetorotational instabilities, and thermal instabilities. The temperature of the disk decreases with distance from the central object, ranging from several hundred Kelvin in the inner regions to a few tens of Kelvin in the outer regions. This temperature gradient leads to different chemical compositions at different radii, which will eventually influence the composition of any planets that form from the disk. After about 1 million years, the protostar evolves into a Class II object, also known as a classical T Tauri star for low-mass stars or a Herbig IB star for intermediate-mass stars. By this stage, the envelope has largely dissipated, and the star is visible at optical wavelengths, though it is still surrounded by a substantial circumstellar disk. Class II objects have spectral energy distributions that peak in the near-infrared or optical range, reflecting the temperature of the central star. However, they also show significant excess emission at infrared wavelengths, indicating the presence of the circumstellar disk. The total luminosity of a Class II object is typically a few tenths to a few solar luminosities, lower than for a Class I protostar. This decrease in luminosity reflects the decrease in the accretion rate, which is typically about 10^8 to 10 solar masses per year for a Class II object. Class II objects are still accreting material, but at a much lower rate than earlier stages. The accretion is no longer spherical, but occurs primarily through the disk. This disk accretion is thought to be driven by magnetic fields that connect the star to the disk, channeling material along magnetic field lines onto the stellar surface. The temperature at the center of a Class II object continues to rise as it contracts. For low-mass protostars, those that will become stars like our Sun or smaller, the central temperature eventually reaches about 10 million Kelvin, hot enough for hydrogen fusion to begin. At this point, the object transitions from a protostar to a pre-main sequence star. For higher-mass protostars, the evolution is more rapid, and they may begin hydrogen fusion while still actively accreting. These objects transition directly from the protostellar phase to the main sequence, without passing through a distinct pre-main sequence phase. The final stage in this classification scheme is the Class III object, or weak-lined T Tauri star. These objects have very little circumstellar material left, with only a tenuous disk or debris disk remaining. They are no longer accreting significant amounts of material and are evolving toward the main sequence primarily through gravitational contraction. Class III objects have spectral energy distributions that are similar to main sequence stars of the same temperature, with little or no excess emission at infrared wavelengths. This indicates the absence of a substantial circumstellar disk. The transition from a Class II to a Class III object involves the dispersal of the circumstellar disk. This process is not fully understood, but is thought to involve several mechanisms, including accretion onto the central star, photoevaporation by ultraviolet radiation from the star, and the formation of planets. The timescale for disk dispersal is typically a few million years, though it can vary significantly depending on the mass of the star and the properties of the disk. Some stars retain their disks for 10 million years or more, while others lose their disks in less than 1 million years. The presence or absence of a disk has important implications for planet formation. Planets are thought to form from the material in the circumstellar disk, so the lifetime of the disk sets an upper limit on the time available for planet formation. Throughout the protostellar phase, the object's luminosity comes from two sources: the gravitational potential energy released as material falls onto the star accretion luminosity, and the thermal energy released as the star contracts, contraction luminosity. The relative importance of these two sources changes over time, with accretion luminosity dominating in the early stages and contraction luminosity becoming more important later. The total luminosity of a protostar can be quite variable, especially in the earlier stages when accretion is episodic. Flares in luminosity, known as FU Orionis events, can occur when a large amount of material suddenly falls onto the star, increasing its brightness by a factor of 100 or more for decades or even centuries. These FU Orionis events are thought to be triggered by instabilities in the circumstellar disk, which cause a sudden increase in the accretion rate. They are more common in the earlier stages of protostellar evolution, when the disk is more massive and more unstable. The variability of protostars is not limited to these dramatic FU Orionis events. Most protostars show some level of variability on timescales ranging from days to years. This variability can be caused by various factors, including changes in the accretion rate, rotation of the star, which brings star spots in and out of view, and flares associated with magnetic activity. The magnetic fields of protostars play a crucial role in their evolution. These fields are thought to be generated by dynamo action in the convective outer layers of the star, similar to the process that generates the Sun's magnetic field. The magnetic fields of protostars are typically much stronger than the Sun's, with field strengths of thousands of Gauss compared to the Sun's few Gauss. These strong fields can have a significant impact on the accretion process, channeling material onto the star along magnetic field lines and driving powerful outflows. The magnetic fields also cause the star to rotate more slowly than would be expected based on the conservation of angular momentum during contraction. This process, known as magnetic braking, transfers angular momentum from the star to the surrounding material, preventing the star from spinning up to break-up velocity as it contracts. As we continue our deliberately monotonous exploration of stellar evolution, let us now examine the pre-main sequence phase, when a star is born, but is still settling into its long-term stable configuration. Part 4, Pre-main sequence evolution. After the protostellar phase, a young star enters the pre-main sequence, PMS phase of its evolution. During this phase, the star is no longer accreting significant amounts of material, but it has not yet reached the stable configuration of a main sequence star. Instead, it is still contracting under its own gravity and deriving most of its energy from this gravitational contraction. The pre-main sequence phase begins when the surrounding envelope of material has been mostly accreted or dispersed, leaving the young star visible at optical wavelengths. For a star like our Sun, this occurs about 1 million years after the beginning of collapse. Pre-main sequence stars are larger and more luminous than they will be on the main sequence. A PMS star with the mass of our Sun might have a radius 2 to 3 times larger than the Sun's current radius, and a luminosity 2 to 3 times greater. This is because the star has not yet fully contracted to its final size. The evolution of a pre-main sequence star can be visualized on a Hertzsprung-Russell diagram, which plots stellar luminosity against surface temperature. PMS stars follow distinctive tracks on this diagram, known as Hayashi tracks and Henny tracks, named after the astronomers who first calculated them. Let's explore these evolutionary tracks in more detail. The Hayashi track, named after the Japanese astronomer Chashiro Hayashi, represents the evolution of a fully convective pre-main sequence star. On the HR diagram, it appears as a nearly vertical line, with the star's surface temperature remaining almost constant, while its luminosity decreases as it contracts. The reason for this behavior lies in the physics of fully convective stars. In such stars, the temperature gradient is determined by the adiabatic lapse rate, which depends only on the composition of the star and not on its size. As the star contracts, its central temperature increases, but its surface temperature remains nearly constant. The Hayashi track represents the coolest temperature at which a star of a given mass can be in hydrostatic equilibrium. If a star were to cool below this temperature, it would no longer be able to support itself against gravity and would contract rapidly until it heated up to the Hayashi track temperature. A low-mass PMS star, less than about 0.5 solar masses, evolves almost entirely along a Hayashi track. This is because such stars remain fully convective even after reaching the main sequence. Their evolution is a simple process of contraction along the Hayashi track until they reach the main sequence. A star of intermediate mass, between about 0.5 and 3 solar masses, begins its PMS evolution on a Hayashi track, but then transitions to a Henny track. The Henny track, named after the American astronomer Louis G. Henny, represents the evolution of a star with a radiative core and a convective envelope. On the HR diagram, the Henny track appears as a nearly horizontal line, with the star's luminosity remaining nearly constant while its surface temperature increases as it contracts. This behavior is due to the changing opacity of the star's outer layers as it contracts and heats up. The transition from the Hayashi track to the Henny track occurs when the star's central temperature becomes high enough for the core to become radiative rather than convective. This happens because the opacity of the stellar material decreases with increasing temperature, making radiative energy transport more efficient than convective transport. For a star like our Sun, this transition occurs when the central temperature reaches about 1 million Kelvin, which happens about 10 million years after the beginning of collapse. At this point, the star has contracted to about 3 times its final radius and has a luminosity about 3 times its main sequence value. After the transition to the Henny track, the star continues to contract, with its surface temperature increasing while its luminosity remains nearly constant. This phase lasts for about 20 million years for a star like our Sun, during which time the star contracts to about 1.5 times its final radius. High-mass stars, more than about 3 solar masses, evolve so rapidly that they have little or no pre-main sequence phase. They begin hydrogen fusion while still accreting material and move directly to the main sequence. Their evolution is dominated by the Henny track, with little or no time spent on the Hayashi track. The length of the pre-main sequence phase depends strongly on the star's mass. A star like our Sun spends about 30 million years in the PMS phase, while a star with 0.1 solar masses might spend 100 million years or more in this phase. In contrast, a star with 10 solar masses might spend less than 100,000 years as a PMS star. This inverse relationship between mass and PMS lifetime is due to 2 factors. First, more massive stars have more gravitational potential energy to release as they contract, allowing them to reach the temperatures required for hydrogen fusion more quickly. Second, more massive stars have higher central temperatures for a given contraction factor, again allowing them to reach fusion temperatures more quickly. During the PMS phase, a star's internal structure gradually changes. Initially, the star is fully convective, with energy transported throughout the star by the physical movement of hot gas. As the star contracts and its central temperature rises, a radiative zone develops in the core, where energy is transported by radiation rather than convection. For stars less than about 0.35 solar masses, the star remains fully convective even after reaching the main sequence. For stars between about 0.35 and 1.5 solar masses, the radiative zone grows outward from the core, eventually encompassing most of the star's interior, with only a thin convective envelope remaining at the surface. For stars more massive than about 1.5 solar masses, the radiative zone encompasses almost the entire star, with a small convective core remaining at the center. The development of a radiative core has important implications for the star's evolution. It allows the star to develop a composition gradient, with heavier elements concentrated toward the center. This gradient affects the star's subsequent evolution, particularly during the post-main sequence phases. As a pre-main sequence star contracts, its central temperature gradually rises. When the temperature reaches about 10 million Kelvin, hydrogen fusion begins in the core through the proton-proton chain reaction. For stars more massive than about 1.3 solar masses, the CNO cycle becomes the dominant fusion process once the temperature exceeds about 17 million Kelvin. The onset of hydrogen fusion does not immediately halt the star's contraction. Instead, The fusion rate gradually increases as the star continues to contract, until the energy generated by fusion balances the energy radiated from the star's surface. At this point, the star has reached hydrostatic equilibrium and has joined the main sequence. Throughout the pre-main sequence phase, young stars exhibit various forms of activity. They may have strong magnetic fields, which interact with any remaining circumstellar material to produce X-ray emission, star spots analogous to sunspots, but often much larger, and flares. They may also drive powerful stellar winds, which can shape the surrounding interstellar medium and affect the formation of planets in the circumstellar disk. The magnetic activity of PMS stars is thought to be driven by the same dynamo mechanism that operates in the Sun, but with greater efficiency due to the star's faster rotation and deeper convective zone. This activity can have a significant impact on the star's environment, including any planets that may be forming in the circumstellar disk. The stellar winds of PMS stars are typically much stronger than those of main sequence stars of the same mass. These winds can remove a significant amount of angular momentum from the star, causing it to rotate more slowly than would be expected based on the conservation of angular momentum during contraction. The winds can also interact with the surrounding interstellar medium, creating bubbles or shells of material around the star. In regions where many young stars are forming, these bubbles can overlap, creating complex structures in the interstellar medium. Many pre-main sequence stars also exhibit variability in their brightness. This variability can be regular, caused by star spots rotating in and out of view, or irregular, caused by changes in the accretion rate or by flares. The study of this variability provides valuable information about the properties and behavior of young stars. T Tauri stars, named after the prototype star T Tauri in the constellation Taurus, are a class of variable PMS stars with masses similar to or less than the Sun. They are characterized by irregular variations in brightness, strong emission lines in their spectra, and excess infrared emission indicating the presence of a circumstellar disk. T Tauri stars are divided into two subclasses: classical T Tauri stars, CTTS, and weak-lined T Tauri stars, WTTS. CTTS are still actively accreting material from their circumstellar disks, as evidenced by strong emission lines and significant infrared excess. WTTS have weaker emission lines and less infrared excess, indicating that they have largely stopped accreting, and their disks are in the process of dispersing. Herbig IB stars are the higher mass counterparts of T Tauri stars, with masses between about 2 and 8 solar masses. Like T Tauri stars, they are PMS stars surrounded by circumstellar disks, but they are hotter and more luminous. They are named after the American astronomer George Herbig, who first identified them as a distinct class of objects. The study of PMS stars provides valuable insights into the early stages of stellar evolution and the formation of planetary systems. By observing stars at different stages of the PMS phase, astronomers can piece together the sequence of events that leads from a collapsing cloud fragment to a stable main sequence star with a planetary system. As we continue our somnolent journey through stellar evolution, let us now turn our attention to the main sequence, the longest and most stable phase in the life of a star. Part 5, the main sequence, stellar adulthood. The main sequence is the stage of stellar evolution where a star spends most of its life. It is characterized by the stable fusion of hydrogen into helium in the star's core, which generates enough energy to balance the inward pull of gravity. This state of equilibrium allows a star to maintain nearly constant properties for millions or billions of years. A star joins the main sequence when hydrogen fusion in its core produces enough energy to counteract gravitational contraction. For a star like our Sun, This occurs about 30 million years after the beginning of collapse. At this point, the star has reached its final size and will remain at approximately the same radius, luminosity, and surface temperature for the duration of its main sequence lifetime. On the Hertzsprung-Russell diagram, main sequence stars form a distinctive band running from the upper left hot, luminous stars to the lower right cool, dim stars. This band, known as the main sequence, represents the relationship between a star's mass and its observable properties. The position of a star on the main sequence is determined primarily by its mass. More massive stars are hotter and more luminous, appearing in the upper left of the main sequence, while less massive stars are cooler and less luminous, appearing in the lower right. Let's explore this relationship in more detail. The main sequence spans a wide range of stellar properties. At the upper end are O-type stars, with masses 15 to 90 times that of the Sun, surface temperatures of 30,000 to 50,000 Kelvin, and luminosities 10,000 to 1 million times that of the Sun. At the lower end are M-type stars, with masses 0.08 to 0.45 times that of the Sun, surface temperatures of 2,500 to 3,700 Kelvin, and luminosities 0.001 to 0.08 times that of the Sun. Our Sun, a G-type star with a mass of 1 solar mass, a surface temperature of about 5,800 Kelvin, and a luminosity of 1 solar luminosity, falls roughly in the middle of the main sequence. The relationship between a star's mass and its luminosity is quite steep. A star with twice the mass of the Sun is about 16 times more luminous, while a star with half the mass of the Sun is only about 1/10 as luminous. This relationship, known as the mass-luminosity relation, is approximately L, m 3.5, where L is luminosity and m is mass. The mass-luminosity relation can be understood in terms of the physics of stellar interiors. More massive stars have higher central temperatures, which lead to higher fusion rates and thus higher luminosities. The central temperature scales approximately as mr, where m is the star's mass and r is its radius. Since r scales approximately as m 0.7, the central temperature scales as m 0.3. The fusion rate is extremely sensitive to temperature, scaling approximately as T4 for the proton-proton chain and T16 for the CNO cycle. This leads to the steep mass-luminosity relation observed for main sequence stars. The main sequence lifetime of a star is inversely proportional to its mass. More massive stars burn through their hydrogen fuel more quickly and have shorter lifetimes. A star with 10 times the mass of the Sun might spend only 20 million years on the main sequence, while a star with 1/10 the mass of the Sun might remain on the main sequence for more than 1 trillion years, longer than the current age of the universe. Our Sun, with a mass of 1 solar mass by definition, has a main sequence lifetime of about 10 billion years. It is currently about 4.6 billion years old, so it is roughly halfway through its main sequence life. The inverse relationship between mass and main sequence lifetime can be understood in terms of the star's fuel supply and consumption rate. The amount of hydrogen available for fusion is proportional to the star's mass. The rate at which this hydrogen is consumed is proportional to the star's luminosity, which, as we've seen, scales as m 3.5. Therefore, the main sequence lifetime scales as ml, or m/m 3.5, which simplifies to m 2.5. This means that a star with twice the mass of the Sun will have a main sequence lifetime about 5.7 times shorter. During its time on the main sequence, a star fuses hydrogen into helium in its core. There are two main processes by which this fusion occurs: the proton-proton chain and the CNO cycle. The proton-proton chain is the dominant process in stars less massive than about 1.3 solar masses. In this process, two protons hydrogen nuclei combine to form a deuterium nucleus, a proton and a neutron, releasing a positron and a neutrino. The deuterium nucleus then combines with another proton to form a helium-3 nucleus, two protons and one neutron. Finally, two helium-3 nuclei combine to form a helium-4 nucleus, two protons and two neutrons, and two protons. Let's examine the proton-proton chain in more detail. The first step in the chain is the fusion of two protons to form deuterium. Where P is a proton, D is deuterium, E+ is a positron, and nu E is an electron neutrino. This reaction is very slow because it involves the weak nuclear force, which is much weaker than the strong nuclear force that governs most nuclear reactions. The positron quickly annihilates with an electron, producing two gamma rays. The second step in the chain is the fusion of deuterium with another proton to form helium-3. This reaction is much faster than the first step because it involves only the strong nuclear force. The third step in the chain can proceed in several ways, depending on the temperature and density of the stellar core. The most common pathway, known as the PPI branch, involves the fusion of two helium-3 nuclei to form helium-4 and two protons. Two alternative pathways, known as the PPII and PPIII branches, become increasingly important at higher temperatures. In the PPII branch, helium-3 fuses with helium-4 to form beryllium-7, which then captures an electron to form lithium-7, which then fuses with a proton to form two helium-4 nuclei. In the PPIII branch, beryllium-7 fuses with a proton to form boron-8, which then undergoes beta+ decay to form beryllium-8, which then splits into two helium-4 nuclei. The CNO cycle is the dominant process in stars more massive than about 1.3 solar masses. In this cycle, carbon, nitrogen, and oxygen nuclei act as catalysts for the conversion of hydrogen into helium. The cycle begins with a carbon-12 nucleus capturing a proton to form nitrogen-13, which then undergoes beta+ decay to form carbon-13. The carbon-13 captures another proton to form nitrogen-14, which captures yet another proton to form oxygen-15. The oxygen-15 undergoes beta+ decay to form nitrogen-15, which captures a final proton to form oxygen-16. The oxygen-16 then ejects an alpha particle, a helium-4 nucleus, returning to carbon-12 and completing the cycle. Let's examine the CNO cycle in more detail. The first step in the cycle is the fusion of carbon-12 with a proton to form nitrogen-13. The nitrogen-13 is unstable and undergoes beta+ decay to form carbon-13. The carbon-13 then fuses with another proton to form nitrogen-14. The nitrogen-14 fuses with yet another proton to form oxygen-15. The oxygen-15 is unstable and undergoes beta+ decay to form nitrogen-15. Finally, the nitrogen-15 fuses with a proton to form carbon-12 and helium-4, completing the cycle. The CNO cycle is much more temperature-sensitive than the proton-proton chain, with its reaction rate scaling approximately as T16, compared to T4 for the proton-proton chain. This is why it becomes the dominant energy production mechanism in more massive stars, which have higher central temperatures. Both the proton-proton chain and the CNO cycle result in the net conversion of 4 hydrogen nuclei into one helium nucleus, with the release of energy in the form of gamma rays and neutrinos. The gamma rays are absorbed by the surrounding stellar material and eventually re-emitted as lower energy photons, which slowly make their way to the star's surface and are radiated into space. The neutrinos, which interact very weakly with matter, escape directly from the core and carry away about 2% of the fusion energy. The energy released by these fusion reactions is enormous. The conversion of 4 hydrogen nuclei into one helium nucleus releases about 26.7 MeV of energy, which is equivalent to about 6.4 times 1012 joules. While this may seem small, the Sun fuses about 600 million tons of hydrogen into helium every second, releasing about 3.8 times 1026 watts of power. As hydrogen fusion proceeds, the composition of the star's core gradually changes. The hydrogen concentration decreases, while the helium concentration increases. This change in composition affects the core's opacity and equation of state, causing subtle changes in the star's structure and observable properties. For most of a star's main sequence lifetime, these changes are very small. A star like our Sun will increase in luminosity by only about 30% over its entire 10 billion year main sequence lifetime. This increase is due to the gradual rise in the core temperature, which is necessary to maintain the fusion rate as the hydrogen concentration decreases. The increase in core temperature occurs because helium nuclei have a higher charge than hydrogen nuclei, leading to stronger electrostatic repulsion. This requires higher kinetic energies, and thus higher temperatures, for the nuclei to overcome this repulsion and undergo fusion. The gradual increase in luminosity has important implications for the habitability of planets. In our own solar system, the Earth was initially cool enough for water to exist as ice, despite the Sun's luminosity being about 70% of its current value. As the Sun's luminosity increased, the Earth warmed, allowing water to exist as a liquid. In the future, as the Sun's luminosity continues to increase, the Earth will eventually become too hot for liquid water to exist, marking the end of habitability for our planet. As a star approaches the end of its main sequence life, with most of the hydrogen in its core converted to helium, more significant changes begin to occur. The core, now composed mostly of helium, cannot generate energy through fusion, as the temperature is not yet high enough for helium fusion and begins to contract under its own gravity. This contraction releases gravitational potential energy, heating the core and the hydrogen-burning shell around it. The increased temperature in the hydrogen-burning shell leads to an increased fusion rate, which in turn increases the star's luminosity. The extra energy pushes the outer layers of the star outward, causing the star to expand and its surface temperature to decrease. The star is now leaving the main sequence and entering the next phase of its evolution, which depends on its mass. For stars like our Sun, this marks the beginning of the red giant phase, which we will explore in the next section. For more massive stars, the post-main sequence evolution is more complex and can involve multiple stages of nuclear burning. As we continue our deliberately soporific exploration of stellar evolution, let us now examine what happens to stars of different masses after they exhaust the hydrogen in their cores. Part 6, Post-Main Sequence Evolution, Red Giants and Supergiants. After a star exhausts the hydrogen in its core, it can no longer maintain hydrostatic equilibrium through core hydrogen fusion. The core, now composed primarily of helium, begins to contract under its own gravity. This contraction releases gravitational potential energy, heating the core and the hydrogen-burning shell around it. The increased temperature in the hydrogen-burning shell leads to an increased fusion rate, which in turn increases the star's luminosity. The extra energy pushes the outer layers of the star outward, causing the star to expand and its surface temperature to decrease. The star is now evolving off the main sequence and becoming a red giant, or for more massive stars, a red supergiant. The exact path of post-main sequence evolution depends strongly on the star's mass. Let us consider three broad categories: low-mass stars, less than about 2 solar masses; intermediate mass stars, between about 2 and 8 solar masses; and high-mass stars, more than about 8 solar masses. For a low-mass star like our Sun, The transition from the main sequence to the red giant phase occurs over a period of about 1 billion years. As the core contracts and the hydrogen-burning shell heats up, the star's luminosity increases and its radius expands. The surface temperature decreases, causing the star to appear redder. On the Hertzsprung-Russell diagram, the star moves upward and to the right, tracing a path known as the subgiant branch. During this phase, the star's luminosity increases by a factor of about 10, while its radius expands to about 10 times its main sequence value. Let's explore this subgiant phase in more detail. As the hydrogen in the core is exhausted, the core begins to contract. This contraction heats the core and the surrounding layers, causing hydrogen fusion to begin in a shell around the core. This shell burning produces more energy than the previous core burning, causing the star's luminosity to increase. The increased energy output pushes the outer layers of the star outward, causing the star to expand. As the star expands, its surface temperature decreases, following the inverse square root relationship between radius and temperature for a body of constant luminosity. This decrease in surface temperature causes the star to appear redder. The subgiant phase is relatively short-lived compared to the main sequence phase, lasting only about 1 billion years for a star like our Sun. During this phase, the star's core continues to contract and heat up, while the hydrogen-burning shell moves outward through the star. As the hydrogen-burning shell moves outward, it eventually encounters the base of the star's convective envelope. This leads to a brief phase known as the first dredge-up, during which material from the core is mixed into the envelope, changing the surface composition of the star. During the first dredge-up, material that has been processed by nuclear reactions in the core is brought to the surface. This includes helium, which has been produced by hydrogen fusion, and certain isotopes of elements like carbon, nitrogen, and oxygen, which have been affected by the CNO cycle. The result is an increase in the surface abundance of helium and nitrogen, and a decrease in the surface abundance of carbon. After the subgiant phase, the star ascends the red giant branch, RGB, becoming much more luminous and larger. A star like our Sun might reach a luminosity 1,000 times its main sequence value and a radius 100 times larger. At this size, if placed at the center of our solar system, it would extend almost to the orbit of Earth. The ascent of the RGB continues until the core temperature reaches about 100 million Kelvin, at which point helium fusion begins. For stars less than about 2 solar masses, this occurs under degenerate conditions, leading to a phenomenon known as the helium flash. In a degenerate gas, pressure depends only on density, not on temperature. When helium fusion begins, the released energy increases the temperature, but does not immediately expand the core. This leads to a runaway increase in the fusion rate, resulting in a helium flash that releases an enormous amount of energy in a very short time, perhaps as much as 100 billion solar luminosities for a few seconds. Let's delve deeper into the physics of the helium flash. In a non-degenerate gas, an increase in temperature would cause the gas to expand, which would lower the temperature and thus regulate the fusion rate. This negative feedback mechanism ensures stable fusion. In a degenerate gas, however, this mechanism doesn't operate because the pressure doesn't respond to temperature changes. When helium fusion begins in a degenerate core, the temperature increases, which increases the fusion rate. The increased fusion rate leads to a further increase in temperature, which further increases the fusion rate, and so on. This positive feedback loop leads to a runaway increase in the fusion rate, resulting in the helium flash. The helium flash continues until the temperature becomes high enough to lift the degeneracy of the core. Once the degeneracy is lifted, the core can expand in response to the increased temperature, which lowers the temperature and thus regulates the fusion rate. The star then settles into stable helium fusion. However, this energy is absorbed by the surrounding stellar material and does not significantly affect the star's outward appearance. The main effect of the helium flash is to lift the degeneracy of the core, allowing it to expand and cool to a stable helium-burning configuration. After the helium flash, the star settles onto the horizontal branch, where it fuses helium in its core and hydrogen in a shell. During this phase, which lasts about 100 million years for a star like our Sun, the star's luminosity decreases and its surface temperature increases compared to the RGB phase. The horizontal branch gets its name from its appearance on the Hertzsprung-Russell diagram, where it forms a roughly horizontal line extending from the red giant branch toward higher temperatures, to the left on the diagram. The exact position of a star on the horizontal branch depends on its mass and composition. Stars with higher metallicity, a higher abundance of elements heavier than helium, tend to be located on the redder, cooler part of the horizontal branch, while stars with lower metallicity tend to be located on the bluer, hotter part. This is because metals increase the opacity of the stellar material, causing the star to have a larger radius and thus a lower surface temperature for a given luminosity. The horizontal branch is populated by stars of various types, including RR Lyrae variables, which are pulsating stars that serve as important distance indicators in astronomy. These stars have a characteristic pulsation period of about half a day, which is related to their absolute magnitude, allowing astronomers to determine their distance. After exhausting the helium in its core, a low-mass star moves onto the asymptotic giant branch AGB, where it fuses helium in a shell around a core, now composed primarily of carbon and oxygen. It may also continue to fuse hydrogen in a shell further out. This double shell burning phase is unstable, leading to periodic helium shell flashes known as thermal pulses. For intermediate mass stars, between about 2 and 8 solar masses, the evolution is similar but with some important differences. These stars also become red giants after exhausting the hydrogen in their cores, but they do not experience a helium flash. Instead, helium fusion begins under non-degenerate conditions, leading to a more gradual transition to the horizontal branch. The reason for this difference lies in the higher core temperatures of intermediate mass stars. These stars have more massive cores, which contract more rapidly and reach higher temperatures before degeneracy sets in. As a result, helium fusion begins before the core becomes strongly degenerate, avoiding the conditions that lead to a helium flash. Intermediate mass stars also spend less time on the main sequence and evolve more rapidly through the post-main sequence phases. A star with 5 solar masses might spend only about 100 million years on the main sequence, compared to 10 billion years for a star like our Sun. After exhausting the helium in their cores, intermediate mass stars also move onto the asymptotic giant branch. However, they may be able to fuse carbon in their cores before the end of their lives, depending on their exact mass and composition. High-mass stars, more than about 8 solar masses, evolve even more differently. They also become red supergiants after core hydrogen exhaustion, but they proceed through subsequent evolutionary phases much more rapidly. They may spend only a few million years as red supergiants before moving on to more advanced stages of nuclear burning. High-mass stars can fuse elements heavier than helium in their cores, proceeding through a series of nuclear burning stages: carbon burning, neon burning, oxygen burning, and silicon burning. Each of these stages produces progressively heavier elements and lasts for a progressively shorter time. Let's explore these advanced burning stages in more detail. After helium burning, the core of a high-mass star is composed primarily of carbon and oxygen. When the core temperature reaches about 600 million Kelvin, carbon fusion begins, producing elements like neon, sodium, and magnesium. This phase lasts for a few hundred to a few thousand years, depending on the star's mass. After carbon is exhausted in the core contracts again, heating up until neon burning begins at a temperature of about 1.2 billion Kelvin. Neon burning produces elements like oxygen and magnesium and lasts for only a few years. Next comes oxygen burning, which begins at a temperature of about 1.5 billion Kelvin and produces elements like silicon, sulfur, and argon. This phase lasts for only a few months to a year. Finally, silicon burning begins at a temperature of about 2.7 billion Kelvin and produces elements in the iron peak, including iron, nickel, and cobalt. This phase lasts for only about a day before the core is converted to iron and nickel. During these advanced burning stages, the star develops a complex onion-like structure, with different elements being fused in concentric shells around the core. The innermost region contains iron and nickel, surrounded by shells of silicon, oxygen, neon, carbon, helium, and hydrogen, in that order. During the red giant or supergiant phase, a star may lose a significant fraction of its mass through stellar winds. For low and intermediate mass stars, this mass loss is relatively gentle, with wind speeds of a few tens of kilometers per second. For high-mass stars, the winds can be much more powerful, with speeds of hundreds or thousands of kilometers per second, and mass loss rates up to a millionth of a solar mass per year. The material ejected by these winds enriches the interstellar medium with elements produced in the star's interior. This enrichment is an important part of galactic chemical evolution, providing the raw materials for the next generation of stars and planets. The mass loss during the red giant or supergiant phase can have a significant impact on the star's subsequent evolution. For low and intermediate mass stars, it can remove most of the star's envelope, leaving only the core, which becomes a white dwarf. For high-mass stars, it can reduce the star's mass enough to affect the type of supernova it will eventually undergo. As we continue our deliberately monotonous exploration of stellar evolution, let us now examine the final stages in the lives of stars of different masses. Part 7: Stellar Endpoints, White Dwarfs, Neutron Stars, and Black Holes. The final fate of a star depends primarily on its initial mass. Low and intermediate mass stars, less than about 8 solar masses, eventually become white dwarfs, while high-mass stars, more than about 8 solar masses, end their lives as neutron stars or black holes, often after a supernova explosion. Let us first consider the evolution of low and intermediate mass stars after the horizontal branch phase. These stars, having exhausted the helium in their cores, begin to fuse helium in a shell around a core, now composed primarily of carbon and oxygen. They may also continue to fuse hydrogen in a shell further out. This double shell burning phase is unstable, leading to periodic helium shell flashes known as thermal pulses. During these pulses, the star's luminosity and radius can vary significantly. The star is now on the asymptotic giant branch, AGB, so named because its track on the Hertzsprung-Russell diagram asymptotically approaches the red giant branch from the left. Let's explore the AGB phase in more detail. The thermal pulses occur because the helium-burning shell is thin and unstable. As helium fusion proceeds, the shell becomes thinner and hotter, leading to an increase in the fusion rate. This increased energy output causes the shell to expand and cool, which temporarily shuts off helium fusion. The shell then contracts and heats up again, restarting helium fusion and beginning the cycle anew. Each thermal pulse lasts for a few hundred years, with intervals of tens of thousands of years between pulses. During a pulse, the star's luminosity can increase by a factor of 2 or more, and its radius can expand significantly. The thermal pulses have important consequences for the star's evolution. They cause mixing between the core and the envelope, bringing material that has been processed by nuclear reactions to the surface. This process, known as the third dredge-up, following the first dredge-up during the red giant phase and the second dredge-up during the early AGB phase for stars more massive than about 4 solar masses, changes the surface composition of the star. In particular, the third dredge-up brings carbon from the helium-burning shell to the surface. If enough carbon is dredged up, the star's surface can become carbon-rich, with more carbon than oxygen by number. Such stars are known as carbon stars and have distinctive spectra dominated by molecular bands of carbon compounds. The third dredge-up also brings other elements to the surface, including elements produced by the S process, slow neutron capture process. The S process occurs in the helium-burning shell, where neutrons produced by nuclear reactions can be captured by iron and heavier elements, producing elements up to bismuth. These elements are then brought to the surface by the third dredge-up, enriching the star's atmosphere and the material it ejects into the interstellar medium. During the AGB phase, the star loses mass at an increasing rate through stellar winds. These winds, driven by radiation pressure on dust grains that form in the cool outer layers of the star, can remove most of the star's envelope over a period of a few 100,000 years. The mass loss rate during the AGB phase can be as high as 10⁴ solar masses per year, meaning that a star can lose a significant fraction of its mass during this phase. For a star like our Sun, the AGB phase might last for about 1 million years, during which it could lose about half of its mass. The mass loss eventually exposes the hot core of the star, which has a surface temperature of about 100,000 Kelvin. The ultraviolet radiation from this hot core ionizes the previously ejected material, causing it to glow as a planetary nebula. Despite its name, a planetary nebula has nothing to do with planets. The term was coined by William Herschel in the 18th century because these objects appeared as small, round disks similar to planets when viewed through the telescopes of the time. We now know that planetary nebulae are shells of gas ejected by dying stars. Planetary nebulae come in a variety of shapes, from simple spherical shells to complex bipolar structures. The shape of a planetary nebula is determined by several factors, including the star's rotation, the presence of a binary companion, and the interaction of the stellar wind with the interstellar medium. The hot core at the center of a planetary nebula is a white dwarf, the final state for low and intermediate mass stars. A white dwarf is composed primarily of carbon and oxygen, with a thin layer of hydrogen and helium at the surface. It is very dense, with a mass comparable to the Sun compressed into a volume comparable to Earth. Let's delve deeper into the properties of white dwarfs. A typical white dwarf has a mass of about 0.6 solar masses and a radius of about 0.01 solar radii, or about the size of Earth. This gives it a density of about 10⁶ grams per cubic centimeter, or 1,000,000 times the density of water. At this density, a teaspoonful of white dwarf material would weigh about 5 tons. The high density of a white dwarf is due to the absence of nuclear fusion to counteract gravity. Without an energy source to maintain its size, the star contracts until it is supported by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from occupying the same energy state. In a degenerate gas, the Pauli exclusion principle prevents electrons from being squeezed too closely together, providing a pressure that can support the star against gravity. This pressure depends only on density, not on temperature, which is why white dwarfs can remain stable even as they cool. A white dwarf no longer generates energy through nuclear fusion. Instead, it slowly cools over billions of years, radiating away its stored thermal energy. As it cools, its luminosity decreases and its color changes from white to yellow to red, and eventually to black. becoming a cold, dark remnant known as a black dwarf. However, the universe is not yet old enough for any white dwarfs to have cooled to this state. The oldest white dwarfs, formed shortly after the Big Bang, have only cooled to about 4,000 Kelvin and still emit a faint reddish glow. The cooling rate of a white dwarf depends on its mass, with more massive white dwarfs cooling more slowly due to their larger thermal capacity. A typical white dwarf might take about 10 billion years to cool from 100,000 Kelvin to 5,000 Kelvin. The maximum mass for a white dwarf is about 1.4 solar masses, a limit known as the Chandrasekhar limit. Above this mass, electron degeneracy pressure cannot support the star against its own gravity, and it will collapse further. The Chandrasekhar limit is named after the Indian-American astrophysicist Subrahmanyan Chandrasekhar, who first calculated it in 1930. It depends on the composition of the white dwarf, with a value of about 1.44 solar masses for a carbon-oxygen white dwarf. If a white dwarf in a binary system accretes enough material from its companion to exceed the Chandrasekhar limit, it will collapse and undergo a type Ia supernova explosion. These explosions are among the most energetic events in the universe and are important for cosmology because they have a nearly uniform peak luminosity, making them valuable as standard candles for measuring cosmic distances. Now let us consider the evolution of high-mass stars, more than about 8 solar masses after the red supergiant phase. These stars can fuse elements heavier than helium in their cores, proceeding through a series of nuclear burning stages: carbon burning, neon burning, oxygen burning, and silicon burning. Each of these stages produces progressively heavier elements and lasts for a progressively shorter time, while hydrogen burning might last for millions or billions of years. Silicon burning lasts for only about a day before the core is converted to iron and nickel. Iron and nickel have the highest binding energy per nucleon of any elements. Fusing them into heavier elements would require energy rather than releasing it, so nuclear fusion cannot proceed beyond this point. With no source of energy to counteract gravity, the core collapses. The collapse occurs extremely rapidly, with the core shrinking from about the size of Earth to about 10 kilometers in less than a second. The infalling material reaches speeds of up to a quarter of the speed of light before hitting the incompressible core, creating a shockwave that propagates outward. This shockwave, energized by neutrinos produced in the collapsing core, expels the outer layers of the star in a supernova explosion. A type II supernova can briefly outshine an entire galaxy, releasing as much energy in a few weeks as the Sun will emit over its entire 10 billion-year lifetime. Let's explore the physics of a core collapse supernova in more detail. As the iron core of the star collapses, the density increases to the point where electrons are forced to combine with protons, forming neutrons and neutrinos. This process, known as electron capture or inverse beta decay, removes the electrons that were providing degeneracy pressure, accelerating the collapse. It also produces an enormous number of neutrinos, which carry away about 99% of the supernova's energy. As the collapse continues, the core density increases to the point where neutron degeneracy pressure becomes significant. This pressure, similar to electron degeneracy pressure, but involving neutrons instead of electrons, can halt the collapse if the core mass is not too large. The sudden halt of the collapse creates a shockwave that propagates outward. However, this shockwave stalls before it can expel the outer layers of the star. The exact mechanism by which the shockwave is revived is not fully understood, but it is thought to involve energy deposition by neutrinos produced in the collapsing core. Once the shockwave is revived, it expels the outer layers of the star at speeds of thousands of kilometers per second. The material ejected in a supernova explosion is enriched with heavy elements produced both during the star's life and during the explosion itself. This material disperses into the interstellar medium, where it can eventually be incorporated into new stars and planets. Indeed, most of the elements heavier than helium in our bodies and our planet were produced in stars and dispersed by supernovae. The fate of the core depends on its mass. If the core mass is between about 1.4 and 3 solar masses, it becomes a neutron star. A neutron star is incredibly dense, with a mass greater than the Sun compressed into a sphere only about 20 kilometers in diameter. The density at the center of a neutron star is comparable to that of an atomic nucleus. Let's explore the properties of neutron stars in more detail. A typical neutron star has a mass of about 1.4 solar masses and a radius of about 10 kilometers. This gives it a density of about 1014 grams per cubic centimeter, or 100 trillion times the density of water. At this density, a teaspoonful of neutron star material would weigh about 5 billion tons. The structure of a neutron star is complex, with several distinct layers. The outer layer, or crust, is composed of a lattice of nuclei and degenerate electrons, similar to the material in a white dwarf but much denser. Below the crust is the outer core, composed primarily of neutrons with a small fraction of protons and electrons. The inner core, which makes up most of the neutron star's mass, is composed of a neutron superfluid, possibly with exotic states of matter at the very center. Neutron stars are supported against further collapse by neutron degeneracy pressure. They have extremely strong magnetic fields, typically 1 trillion times stronger than Earth's magnetic field, and they rotate rapidly, with periods ranging from milliseconds to seconds. The rapid rotation and strong magnetic field of a neutron star can produce beams of radiation that sweep across space like a lighthouse beam. If one of these beams crosses our line of sight, we observe regular pulses of radiation, leading to the classification of such neutron stars as pulsars. Pulsars are incredibly precise timekeepers, with periods that are stable to 1 part in 1014 or better. This precision makes them valuable for various astronomical applications, including tests of general relativity and the detection of gravitational waves. If the core mass exceeds about 3 solar masses, not even neutron degeneracy pressure can support it against gravity, and it collapses to form a black hole. A black hole is a region of spacetime where gravity is so strong that nothing, not even light, can escape from it once it passes the event horizon. The size of a black hole is characterized by its Schwarzschild radius, which is proportional to its mass. For a black hole with 10 solar masses, the Schwarzschild radius is about 30 kilometers. Despite their small size, black holes can have a significant influence on their surroundings through their gravitational effects. Let's explore the properties of black holes in more detail. A black hole is characterized by just 3 parameters: its mass, its angular momentum or spin, and its electric charge. This property, known as the Noether theorem, means that all other information about the matter that formed the black hole is lost when it crosses the event horizon. The event horizon of a black hole is the boundary beyond which nothing can escape. It is not a physical surface, but a mathematical boundary defined by the point at which the escape velocity equals the speed of light. Inside the event horizon, spacetime is so curved that all paths lead inward toward the singularity at the center of the black hole. The singularity is a point of infinite density where the known laws of physics break down. According to general relativity, all the mass of the black hole is concentrated at this point. However, it is believed that a yet-to-be-developed theory of quantum gravity would provide a more accurate description of the singularity. Black holes can grow by accreting matter or by merging with other black holes. When matter falls into a black hole, it typically forms an accretion disk around the black hole, before crossing the event horizon. The matter in this disk is heated to millions of degrees by friction, causing it to emit radiation across the electromagnetic spectrum, particularly in the X-ray range. The merger of two black holes releases an enormous amount of energy in the form of gravitational waves, ripples in spacetime that propagate at the speed of light. These gravitational waves were first directly detected in 2015 by the LIGO and Virgo collaborations, confirming a major prediction of Einstein's theory of general relativity. Black holes come in several size categories. Stellar mass black holes, with masses ranging from about 3 to 100 solar masses, are formed from the collapse of massive stars. Intermediate mass black holes, with masses ranging from about 100 to 100,000 solar masses, may form from the merger of stellar mass black holes or from the direct collapse of very massive stars. Supermassive black holes, with masses ranging from millions to billions of solar masses, are found at the centers of most galaxies, including our own Milky Way. The formation of supermassive black holes is not fully understood. They may form from the merger of smaller black holes, from the direct collapse of massive gas clouds in the early universe, or from the collapse of dense star clusters. Whatever their origin, they play a crucial role in galaxy evolution, influencing the distribution of stars and gas through their gravitational effects and through the energy released by matter falling into them. As we conclude our deliberately soporific journey through the life cycle of stars, let us reflect on the cosmic significance of stellar evolution. The elements produced in stars and dispersed by stellar winds and supernovae are the building blocks of planets, moons, and life itself. In a very real sense, we are made of stardust, the ashes of long-dead stars that enriched the interstellar medium billions of years ago. The study of stellar evolution connects us to the vast cosmic cycles of birth, life, and death that have been unfolding for billions of years and will continue long after we are gone. It reminds us of our place in the universe, tiny and ephemeral, yet connected to the grandest scales of space and time through the matter that makes up our bodies, and the light that reaches our eyes from distant stars. As you drift off to sleep, perhaps contemplating the life cycles of the stars twinkling above, remember that you are witnessing a process that has been ongoing for billions of years and will continue for billions more. The universe operates on timescales far beyond human comprehension. Yet through science, we can glimpse these cosmic cycles and understand our place within them. Conclusion: we have journeyed through the complete life cycle of stars, from their birth in cold molecular clouds to their eventual fate as white dwarfs, neutron stars, or black holes. We have explored the physics that governs their formation, evolution, and death, and we have seen how these processes connect to the broader cosmic cycles of matter and energy. Stars are not eternal, unchanging objects, but dynamic systems that evolve over time. They are born, they live, and they die, each following a path determined primarily by their initial mass. In their deaths, they seed the universe with the elements necessary for the formation of planets and life, continuing the grand cycle of cosmic evolution. As you fall asleep to this cosmic lullaby, remember that the atoms in your body were forged in the hearts of stars that lived and died billions of years ago. We are, in the most literal sense, children of the stars, connected to the cosmos through the very substance of our being.